Performance evaluation of a photovoltaic pumping system in Funaab community. Abstract: the need for constant renewable supply of electricity for effective pumping of water at low cost is highly needed to provide a constant supply of water for Funaab community. It is important to understand the source of water and consumption pattern to ensure the sustainability of water supply, and also to reduce its costs. The design, installation, and performance evaluation of a photovoltaic pumping system in Funaab community was carried out. The water demand for the site and daily solar insolation data obtained using Meteonorm software were determined. The component parameters for the PV pumping system were designed to include the pump flow rate and the hydraulic power, the hydraulic head, power rating of the PV module, orientation and direction of the PV module. Experiments to acquire a relationship between photovoltaic pump system outputs and solar radiation intensity at different times during the day were carried out to determine periods of maximum pumping efficiency. The maximum discharge logged 0.162 m3/h was obtained between 11 am to 2 pm at the PV power output of 727.5 W/m2 with a 300 W solar module connected to a DC pump discharging at 24.5 m water head. The system operated approximately 8 hours in the month of October. Although the initial cost to set up a PV pumping system is high, but with the little maintenance cost for years, it is revealed that PV-based water pumping system is a suitable and feasible option for domestic use and farm irrigation systems in Funaab community. Keyword: PV module, DC pump, power consumption, solar insolation, pump discharge. 1. Introduction. Like most other communities in Nigeria, the energy situation in Funaab community is extremely critical, so the electricity generation from alternative sources has become a much focused need. Funaab community is blessed with renewable energy resources, and the availability of alternative energy creates opportunities for utilization in the power sector. Among different renewable energy sources like solar, wind, biomass, and others, the abundant availability of solar energy makes it the most promising one for Funaab community. Funaab community is located in Ogun State at the state capital Abeokuta, 7 degrees 9 minutes 39 seconds north, 3 degrees 20 minutes 54 seconds east Nigeria, which is an ideal location for abundant solar radiation with average solar radiation of about 4.5 kWh/m2/day, 16.2 mJ/m2/day. The utilization of the photovoltaic system for water pumping is appropriate, as there is often a natural relationship between the availability of solar energy and the water requirement. The water requirement increases during hot weather periods when the solar radiation levels are highest and the output of the solar array is at a maximum. Photovoltaic water pumping systems are particularly suitable for water supplies to the irrigation system used in Funaab farmlands, and also for other domestic uses. Therefore, renewable solar energy-based off-grid electrification can be an alternate option for providing electricity in Funaab community where no reliable constant electricity supply is available. Given an average solar radiation level of about 4.5 kWh, m2 per day, and the prevailing efficiencies of commercial solar electric generators, then if solar collectors or modules were used to cover 1% of Funaab's land area of 100 square kilometers, it is possible to generate 1850 x 103 GWh of solar electricity per year, which is over 100 times the current grid electricity consumption level in the country. Though the installation cost of a solar-powered pumping system is more than that of gas, diesel, or propane-powered generator-based pumping system, it requires far less maintenance cost. 9. However, by comparing installation costs, including labor, fuel costs, and maintenance costs over 10 years with other conventional fuel-based pumping systems, the solar PV water pumping system can be a suitable alternate option. 8. This system has the added advantage of storing water for use when the sun is not shining, eliminating the need for battery, electricity, and reducing overall system costs. 2. Materials and methods. 2.1 Water demand design. The building consists an average of 30 occupants per day with an approximate water usage of 14 liters per person. Assuming increase in occupants by 25%, total number of occupants equals 30 times 1.25 equals 37.5 equals 38. Therefore design population equals 38 persons. The daily water demand was calculated using the formula equals times 1, where Q equals daily water demand, liters. CP equals per capita consumption per day. DP equals design population. Substituting a daily water requirement of 14 liters per person per day in equation above, we have Q equals 14 x 38 equals 532 liters per day equals 0.53 m3/day. 2.2 Water storage design. The purpose of the battery-less PV water pumping system is storing water instead of electrical energy. The disadvantages of employing battery storage is requiring a complex control system, considerably increases in the cost of implementing the system and more maintenance burden of PV water pumping system. The water tank size was designed to be 3 times of peak water demand 16. Water storage size would be equals 3 times 532 liters equals 1596 liters equals 1.6 cubic meters. 2.3 Pump design. Pump flow rate. The pump flow is estimated via dividing daily water demands by PSH. PSH represents peak sun hours every day. Using the sunshine data from the area, the peak sun hours is 4.5 hours, which is used in the design 16. The pump flow rate Q is then determined as follows. Pump total dynamic head. The total dynamic head, TDH, for a pump is the sum of the vertical lift, pressure head, and friction loss. Friction losses apply only to the piping between the point of intake, inlet, and the point of storage, i.e. the storage tank. Therefore, friction losses between the storage tank and the point of use are independent from the pump and do not need to be accounted for when sizing the pump 16. TDH equals vertical lift plus pressure head plus friction losses, 3. Vertical lift equals vertical distance between the water surface at the intake point and the water surface at the delivery point, the tank's water surface. Vertical lift equals 80 feet equals 24.3 m. Pressure head equals pressure at the delivery point in the tank. There is no pressure at the delivery point, the water surface in the tank, so pressure head equals 0 feet. Friction loss is the loss of pressure due to the friction of the water as it flows through the pipe. Friction loss is determined by 4 factors: the pipe size, inside diameter, the flow rate, the length of the pipe, and the pipe's roughness. Due to the relatively close proximity of the intake point and the storage tank, the total friction losses in the pipeline would be minimal. As such, approximately 360 inches of 12-inch diameter PVC pipe will be used to convey water from the source to the tank. The friction loss for 1/2-inch pipe conveying 1.11 GPM is approximately 1.14 feet of head loss per 100 feet of pipe. Therefore, the total estimated friction loss for 30 feet of pipe is calculated below. 1.14, 100, times 30 feet equals 0.342 feet friction head. Total dynamic head TDH equals 80 feet plus 0 feet plus 0.342 feet equals 80.342 feet equals 24.5 m. Pump power requirement. The hydraulic energy required of the pump can also be calculated as in below. E equals 3.6 times 106, 4. Where E equals hydraulic energy required, kilowatt-hour/day. Equals density of water, 1000 kg/m3. G equals gravitational acceleration, 9.81 m2. H equals total hydraulic head, 24.5 m. V equals volume of water required, 1.5 m3/day. By putting above all values, equation reduces as shown below. E equals 1000, 3 times 9.81, 2 times 24.5 times 1.53 3.6 times 106 equals 0.10014 kilowatt-hour/day equals 100.1 Wh/day. 2.4 Sizing of PV panel. Sizing and selection of PV panels. The size of panels to be used depends on the amount of power that is required, in watts, the time it operates, in hours, and the amount of energy available from the sun in a particular area. The first two parameters are based on the project requirement, while the third depend on the location. The size of a PV array was calculated by using the equation below. The solar array power required, kWp kilowatt peak. Orientation and direction of the PV array. Orientation of the PV array is one of the most important aspects of the site assessment. For any surface, the maximum available radiation is obtained when the sun's incidence is normal to the plane of the plate. This is approximately so at the noon of the location. In order not to be tracking the sun every now and then, it is necessary to find a fixed value of tilt that will absorb radiation higher than that possible were the surface horizontal through the day, though not as high as when hourly tracking of the sun rays is adopted. For optimum tilt angle, 0 + 10 degree for locations with latitude 8.5 degrees north. Therefore the optimum possible tilt angle for Abeokuta is approximately 17.2 degrees 1. Therefore the solar PV array will be tilted at this angle with the help of clinometer. Incident solar radiation to the PV array gives the input power, watts, to the system given by 2.5 materials used. The Table 2 shows a list of the materials used for the installation of the PV pumping system. Materials. Quantity. Installation process. The installation process is shown in plates 1 to 5. The PV panels is mounted on a erected metal frame support facing a location where it receives maximum sunlight throughout the year, avoiding trees or other obstructions that could cast shadows on the solar panel and reduce its output. The PV panel is connected directly to the PWM charge controller that was nailed to the wall. The charge controller is connected to the battery regulator, and the output of the charge controller is connected to a switch box which is also connected to the pump. A 12 volts positive displacement submersible DC pump was selected to pump water from the reservoir at a depth of 1.8 m below ground surface. The pump was connected to the 1/2 PVC pipe. The PVC pipe other end connects to a digital flow meter to allow the pumped water flow through the flow meter, leaving through the PVC pipe and dumped into the tank. The pipes used for the water transfer between the reservoir and the tank are 1/2 PVC. 3 results and discussion. 3.1 Results. During the course of testing, the following parameters were recorded to evaluate the performance of the photovoltaic pumping system and determine the pump discharge rate at every pumping hour. Fig 2 shows the motor power consumption at pumping discharge rate during a selected day in the month of October. It could be seen that 8 HRS of the day, the solar radiation was 430, the power delivered to the pump was 26.2 watts. The solar radiation increases gradually to maximum value of 40.2 at the midday. This is followed by decrease in solar intensity to a value of 28.2 at 17 HR of the day. Figure 3 shows the variation of pump discharge during the selected day in the month of October when solar radiation was highest for Funaab community. Fig 4, hourly average radiation, derived from Meteonorm software, through a selected day in the month of October. The graphical representation of solar radiation and discharge with respect to time shows that the discharge has been increased from morning to middle of the day or noon. After that, discharge will be decreasing. It clearly indicates that the peak solar radiation in October will provide sufficient energy for maximum discharge. This discharge is higher than the prescribed 0.11823/H. Hourly solar radiation average was derived from Meteonorm database for area under investigation. Hourly solar radiation is shown in graphical figure 4.3. The highest solar radiation 727.5/2 is found at mid of day, and variation in the pattern shows the absence of clear sky condition. The sufficient radiation availability shows the sufficient running power availability for the PV array generation which fulfill the energy requirement of submersible pump. Figure 5 represents time V/S array efficiency, EA, subsystem efficiency, ES, and overall efficiency, EO. It shows that all efficiencies will be increased from morning time approximately 8 am to 9 am and it is constantly up to 5 pm after that abruptly decreases. It means system is designed for constant efficiency and it is clear that these efficiencies depends on the solar radiation intensity availability or availability of solar radiation for maximum power output from the PV array. Linear relationships concerning solar radiation values, W/M2, with both pump discharge, M3/H, and DC motor power consumption, Watt, were obtained using curve fitting equation, 150 = R = 750, as illustrated in Fig. 4.5, 4.6, respectively. For conclusion. The conclusions of this study are found as follows. The system is economically feasible in interior areas where no electricity or it is an alternate source of electricity. The initial cost is high, but with the little cost of maintenance over the years, it becomes the best option compared to other methods of water pumping system. It is a good alternate because the demand is in the face of solar radiation availability. Although this study could not correctly predict the degree of suboptimal performance of all the subsystems due to limitations of data acquisition methods, it highlights the critical need to operate the PV system at its design parameters. Other than physically creating the extra head, reducing the total array power utilized for pumping appears another plausible solution for improving the overall system efficiency. The excess power could be diverted to some other operations. However, for any such design change, a few aspects need careful consideration. The PV systems are designed taking into account the daily and mostly hourly variations in solar-related parameters. The pumping systems are designed such that water is available for maximum hours of sunshine during the day. It is possible that excess power is available during certain hours of the day and the reduced array power may not always be adequate to pump water at times when the irradiance is low.